Hello and welcome to our module on acid-base indicators. Today we'll be covering what an acid-base indicator actually is, some common examples that you need for your senior studies, and how the concept of acid-base indicators relates to the concept of the pKa. So before we start, it's very important to set up some context. So an acid-base indicator at the very basic level is just a substance that changes color depending on the pH that it's in. Usually, acid-base indicators are a combination of an acid and a conjugate base, or a base and a conjugate acid. One of these ions will be intensely colorful in aqueous solution. So what exactly does that mean? We'll go with our first example. Let's assume that our acid-base indicator is a combination of an acid and a conjugate base. We'll pretend that the acid is maybe colorless and the conjugate base is intensely red in color. So if there's equal amounts, so in a pH where there's a favorable amount of both the acid and the conjugate base, it might give like a pink kind of color, so a combination of colorless and red. However, if we put it in a pH or a solution that has a pH that favors the conjugate base, so there's a lot of it, that solution will appear bright red. We can then judge the color and then the acid profile. So basically every acid-base indicators have a range, a pH range in which they'll change the color. We can then go off that and the color that we observe to give us a rough measure of the pH. In practice, we use universal indicators as a rough indicator of whether the substance is acidic or basic. We then qualify this using further indicators and you'll see some examples in later slides of how acidic or how basic a substance is. As you might have guessed, this is a qualitative measure of the pH. So we're not getting a number, we're just getting a rough measure based on a color. So it can't be quantitative. Quantitatively, we can attempt to measure the pH from an acid-base indicator using colorimetry. It's not essential for you to understand for your senior studies, but essentially you have a machine that can measure the intensity of a color. So as you might have guessed, you calibrate it based on a wide variety of pHs, and then when you give it a solution to analyze, it'll be able to roughly tell you the pH of the solution. You can also just use a pH meter to work out the pH. Here we have an example of a very common acid-base indicator. So this is litmus paper. Essentially what you do is you rip one of those amber sheets off, put them into your solution, and then it will very quickly change color. The chart that you can see has a range of colors that correspond to a relevant pH. Based on the color changes that you observe, you can then look at the chart, whichever color best matches that color, that will give you a rough idea on the pH. In the lab, you'll then be asked to confirm this using a pH meter. So basically, this is just a probe that you put in solution, and that gives you a very accurate reading of the pH. So here we have some common examples of acid-base indicators that you will come across. The bad news is that you will need to know this table pretty well, but the good news is, firstly, it's not too bad. It looks really intimidating, but it's actually not too bad. So one thing I tried to do is learn it systematically. So I'd go off the color changes. So thionyl blue and methyl orange, for example, are both red in an acidic solution and yellow in a basic solution. The pH ranges differ, so I just memorize the pH ranges. And then using that kind of system, you can basically pair them and memorize the whole table pretty quickly. Also, we built in flashcards, so just do those and hopefully it'll stick. The ones in X with a red X next to them are the most common ones that I've seen. So those are the really high yield ones. Methyl red, litmus, bromothymol blue, and phenolphthalein. It does differ school to school and practical exam to practical exam, but in most cases, those are the ones that people use. So yeah, really remember those. One thing I want you to understand is the pH range. So we're going to pick on bromophenol blue, 3.0 to 4.6. So what exactly does that mean? One thing I try to use to make sense of it is kind of using circular logic. So bromophenol blue changes color between 3.0 to 4.6. For example, if we were to use bromophenol blue to look at the pH of two basic solutions, so distinguish between two basic solutions, which of them is a stronger base and which of them is a weaker base, it would be completely useless because both of the solutions would appear blue. However, if we want to judge if a solution is very acidic, so maybe has a pH of 2, and not too acidic, so maybe has a pH of 5, or maybe neutral even, and has a pH of 7, we can do that with bromophenol blue. So the very acidic solution is less than 3, so it would appear yellow. The neutral or less acidic solution has a pH of greater than 4.6, which is outside the pH range, so it would appear blue. Going off this color change, we can have a fair idea of the pH, or the difference in pH of two solutions. As you can see, we need to strategically pick the acid-base indicator based on where we think the pH of a solution lies. And that's kind of why we use the universal indicator first. That just gives us a general gist of whether the solution is acidic, neutral, or basic. Then using these common qualifying indicators, if you like, you can judge how acidic or how basic or how neutral even a substance is. So now time to relate this concept of the indicator color change with the constant, so the Ka. Over the next two slides, I'm going to take you through an example of an indicator and what happens when it's an acidic solution, and then in the next slide, what happens when this indicator is in a basic solution. There are two ways you can analyze the color change. Firstly, quantitatively, using the actual constant. Secondly, you can also use Le Chatelier's principle. The former you need to know for your exams, the latter is just much easier to understand. So we'll start with the quantitative analysis using the constant. Say we have an indicator, so IN. In this case, this indicator is an acid and it yields a conjugate base in solution. The acid is a bright red color, signified by the hydrogen ion and the red ink, and the conjugate base, when dissolved in solution, is a bright yellow. This indicator has a constant of 8 times 10 to the power of minus 6. We're going to write our formula for the dissociation constant before we start anything. So products over reactants, we get the concentration of the conjugate base, which is yellow, multiplied by the concentration of hydronium, all over the concentration of the original acid. A very interesting thing happens when it's dissolved in an acidic solution with pH of 3. From prior videos, you should remember how to calculate the concentration of hydronium given the pH. As a refresher, use this equation. So if the pH is 3, the concentration of hydronium will be 10 to the power of minus 3. We know that the Ka is 8 times 10 to the power of minus 6. So if we move this to the other side, we get something that looks like this. 8 times 10 to the power of minus 6 over 10 to the power of minus 3 equals the concentration of the conjugate base, so the indicator minus, so the indicator anion, all over the original acidic indicator. This will give you 8 times 10 to the power of minus 3, which is a pretty small number. So that's a number that's less than 1. So it's a fraction. This tells you that the concentration of the bottom number, so the bottom number will be very big and the top number will be less big, if that kind of makes sense. So if I have a fraction and we have a huge bottom number and a not so big top number, that'll give us a very, very small result. Kind of what happens here. Therefore, the concentration of the original acid is greater than the concentration of the conjugate base, and the solution is red in color. Another way of thinking about this is, if it's in an acidic solution with a pH of 3, there's a lot of these hydronium ions floating around. According to Le Chatelier's principle, it's going to resist that change and shift to the other side and make more of this. So same result, it'll just be red. In a similar vein, but a bit different, we're going to now look at what happens when our indicator here is in a basic solution with a pH of 14. Once again, we write our equation for the dissociation constant, which is the conjugate base indicator anion multiplied by the concentration of hydronium all over the concentration of the original acidic indicator. However, this time, this value here is 10 to the power of minus 14, and I showed you how to calculate that in the previous slide. We once again know that the Ka is 8 times 10 to the power of minus 6. So if you move that to the other side, we get something that looks like this. 8 times 10 to the power of minus 6 all over 10 to the power of minus 14. However, this time, this gives you 8 times 10 to the power of 8. So positive 8. And that is a huge number. In the previous slide, it gave you 8 times 10 to the power of minus 3 when it was in a acidic solution, small number. In this case, it gives you 8 times 10 to the power of 8, which is a very, very big number. So if that equals 8 times 10 to the power of 10 to the power of 8, this tells you that this top number here is absolutely massive, and this bottom number is probably not that big. Hence, there is a large concentration of the conjugate base indicator, and not that big a concentration of the original acid, and thus the solution will appear yellow. Another way of analyzing this is Le Chatelier's principle. If we have this equation in a basic solution, so a very strong basic solution as well, it will try and resist the change and form more of the hydronium ion. So it will shift in this direction and consequently make more of this. Same result, the solution will appear yellow. This is just a short summary slide showing these findings. So if the ratio of the conjugate base indicator all over the original acidic indicator is 1, that means that there's equal concentrations, and it'll give you a mixture in color between yellow and red. If it is greater than 1, that means there is more of this, and if it's less than 1, that means it's more of that. And thus the color will change depending on what pH the solution what pH the indicator, is in. Hopefully now you have a pretty good strong understanding of acid-base indicators, the color change, and how this all relates to the dissociation constant. Now, instead of using a fake indicator, we're going to bring this back to real life and present to you our table again of all the really important indicators. The main takeaway that I want you to remember, I don't want you to remember the dissociation constant of each of these indicators. That's a colossal waste of time. The main takeaway that I want you to remember is the lower the pH range, the higher the dissociation constant will be. However, if you have a strong understanding of the explanation that I showed you in regard to our model acid-base indicator, that should be more than enough for your senior studies.